Good afternoon, everyone. First of all, I want to thank the organizing committee for this space and time to share our work that is entitled CONICET-Nanodots, a micromagnetic approach towards enhanced electrochemical performance for supercapacitors. This work was in collaboration with colleagues from University Nacional of Córdoba, from Argentina, and from 2 universities from Chile. I also want to share with you some photos of the city of Cordoba. If you have the opportunity to visit our city, it's highly recommended because of the nice places that you can visit, natural, and the cathedral, as you can see in this first slide. Well, what is our main motivation for this work? Is the the global crisis about energy that means that the scientific community is searching different ways to affront this demand from the development of materials. Among the all materials that are in the interest of the community, supercapacitors is one of the main interests for us because we can contribute from the magnetism. Why magnetic materials could be a nice and an interesting material for efficient supercapacitors? Well, first, because the presence of these nanostructures can increase the surface area and the magnetic properties could lead to enhanced energy density. More or less, faster charge transfer plus reduced internal resistance can be get from improved rate capability. Then we can also expect improved structural stability with the presence of magnetic nanostructures that could lead to enhanced cycle life. And another point that I also want to highlight, that is just some of them, the advantages of using magnetic material is a magnetic field control that we can get from the size and the morphology of this nanostructure and the synergistic effect with other platforms where this nanostructure, magnetic nanostructure, could be used to get tunable properties. So all these advantages could be taken into account when dealing with nanostructures for electrodes in supercapacitors. There are, in the recent years, many evidences about these characteristics and disadvantages. And in this talk, I want to share with you one of the examples that we develop exploring CONI nanostructures for supercapacitor electrodes from 2 points of view, simulations and experimental. From the point of the view of the experimental, we wanted to give realistic morphologies. Because of that, here in the slide number 1, you can see 10 images of CONI dots that were isolated and renderized to get the real edges of these cobalt nickel nanodots. Then we use software that is that had more than 3,000 papers validated with the results. When apply the LLG Landau-Lifshitz-Gilbert to study the dynamic of the magnetization. Here we studied how the composition of the cobalt percentage in the nanostructure affects the magnetic properties. And in order to carry out this goal, what we did is to take the parameter from cobalt and nickel, and before here you can see the equations that lead to the description of the composition for each of the parameters, magnetic parameters of these 2 materials, taking account the exchange length always remains higher than the cubic cell that we use here. The cubic cell that were used were about 2.5 nanometers cubic, and the field, the magnetic field, was applied in the XY direction. On the other side, you can see the experimental setup set up to get these nanostructures, where here you can see a photo of the cobalt nickel powder for one of the compositions. First of all, as a result from the micromagnetic simulation results, you can see on the left the phase diagram for the ideal cobalt nickel, where for coercivity we can see that about 50% of cobalt there is an abrupt jump that is one of the main interested when we compare this result with the real defective cobalt nickel nanodot, where the phase theorem is totally different. You can see here that the monotonic behavior of the cobalt percent for the remnant properties goes up to 80%, and around 90% there is a jump. Meanwhile, from the coercivity, we have a maximum around 60%. So here we have a message from the role of the defect and the effect of the composition in the material to on the magnetic properties. We also studied the magnetization reversal mode, identify the Carli mechanisms where between the S and U modes that were expected, the S mode was dominant, and here you can see on the right which are the reversal magnetization for ideal dot, and the hysteresis loop for nickel and cobalt compared with the pure cases. On the right, you can see how these hysteresis loops are affected by the presence of defects on the edges, leading to the defects that serve as nucleation sites for magnetic domains with opposite direction in the magnetization. We preserve the mechanisms, the S mechanisms of the onion mechanisms here, but on the opposite direction. Also, we studied the dynamic response by FMR, the resonance ferromagnetic studies, applying a pulse to these nanostructures to see which are the dominant modes for the cobalt nickel and the three composition. What we got here, you can see that for the ideal cases are identified two modes. In the first case, the mode number 2 is have a linear dependence. Meanwhile, the mode number 1 is almost constant. On the other side, for defective nanostructure, we can see the presence of three modes. The mode number 2 here have a linear dependence, and meanwhile the mode 2 and mode that we called right and left have almost a constant behavior. So here the defects also impacts not only on the coercivity and remanence, but also in the spin waves modes that we can see here from this study. In order to compare the simulation results with experimental results, we also perform magnetic measurements through the AGF magnetometers that is high sensitivity, and as you can see here for the three composition, the coercivity is almost similar, and in this case we took this comparison around to take the value of the coercivity around 50 millitesla. That is in good agreement with the expected or what we observe from the simulations. This means that even when you simulate one single nanodot of cobalt nickel, this tool is highly powerful to predict the tendency of the experimental magnetic properties for these three compositions in cobalt nickel nanodot. And finally, what we did was to take these powders and perform electrochemical measurements by cyclovoltammetry, where you can see in the black line the matrix, the carbon matrix, and the two other composition with 10% of cobalt nickel. The size of the cobalt nickel were around 5 of 15 millitesla. And on the other side, you can see the electrochemical results by means of cyclic voltammetry, where the black line is from the carbon matrix, and the blue and red lines corresponds to the composition with 10% of cobalt nickel nanodot. What we can see here that is a hybrid supercapacitors, where the role of the nanodots show how the electrochemical performance could be increased by the presence of these nanodots. Good. Here we can see also that the size and the morphology of the nanodots that are on the 10 images on the right panel show that even when they are different effects on the edges from that one we study with micromagnetic simulations, the tensors that we can get from this power tool allow us to predict which is the best composition, or which is the optimum composition when using this material for hybrid supercapacitors. Here, these are different nanodots from the example that we took for the simulation, and are also around 500 nanometers. So as a conclusion, we can say that cobalt nickel nanodots and different composition are promising materials for supercapacitors, hybrid supercapacitor electrodes, where the versatile characteristic of this magnetic material include their remanence and coercivity, and also how the presence of defects can induce the mechanisms of the Carlin reversal mechanisms, but it's not different from the either one. Also, we can expect a change in the direction of this S or onion reversal mechanisms. I can say thank to our institutions that support the investigation, and all the colleagues that take part of this work that are from University from Chile and University Nacional of Córdoba, National University of Córdoba. Thank you very much for your attention.
Thank you very much for the talk and for persistence in presenting it. Unfortunately, we don't have time for questions, so we'll need to move to the next speaker.
Okay, thank you.